Hello my physics students, this is Mrs. Buchanan and this is flip video number 12. We are completing our discussion of Newton's three laws of motion with Newton's third law of motion, action and reaction. So let's visit our big idea. For every force, there is an equal and opposite force. In this flip video, we're going to cover three learning objectives. Define force as a part of an interaction, state and apply Newton's third law of motion, and describe how to identify a pair of action-reaction forces. If you lean over too far, you'll fall. But if you lean over with your hand outstretched and you make contact with a wall, you can do so without falling. When you push against the wall, it pushes back on you. That's why you're supported. Ask your friends, why don't you topple over? How many of them will answer because the wall is pushing on you and holding you in place? Probably not very many people, unless they're physics types like us, realize that walls can push back on us every bit as much as we push back on them. Similarly, kayak paddles that push water backwards are pushed forward by the water. In this example here we see that F sub action equals F sub reaction begins our discussion of interactive pairs. Also, you can see NASA obviously would be very concerned about Newton's third law of motion. To stop or slow down an object, a force must be applied in the direction opposite to that of the object's motion. So our first learning objective, define force as a part of an interaction. In the simplest sense, a force is a push or pull. Looking closer, however, Newton realized that a force is not a thing in itself. A force is always part of a mutual action that involves another force. A mutual action is an interaction between one thing and another. For example, consider an interaction between a hammer and a nail. A hammer exerts a force on the nail and drives it into the board. But this force is only half of the story, for there must also be a force exerted on the hammer to halt it in the process. What exerts this force? The nail does. Newton reasoned that while the hammer exerts a force on the nail exerts a force on the hammer. So in the interaction between the hammer and the nail, there are a pair of forces, one acting on the nail and the other acting on the hammer. Such observations led Newton to his third law, the law of action and reaction. So we want to talk a little bit about here in a few minutes about identifying interaction pairs. But first what I want to do is I want to talk a little bit about stating and applying Newton's third law of motion. Newton's third law describes the relationship between two forces in an interaction. It states that whenever one object exerts a force on a second object, the second object exerts an equal and opposite force on the first object. One force is called the action force, the other force is called the reaction force. It doesn't matter which force we call the action and which one we call the reaction. The important thing is that they're partners in a single interaction and that neither force exists without the other. They're equal in strength and opposite in direction. Newton's third law is often stated, to every action there is always an equal and opposing reaction. In every interaction the forces always occur in pairs. For example, you interact with the floor when you walk on it. You push against the floor and the floor simultaneously pushes against you. Likewise, the tires of a car interact with the road to produce the car's motion. The tires push against the road and the road simultaneously pushes back on the tires. When swimming, you interact with the water. You push the water backward and the water pushes you forward. Notice that the interaction in those examples depend on friction as well. For example, A person trying to walk on ice where friction is minimal may not be able to exert an action force against the ice. Without the action force, there cannot be a reaction force. Thus, there is no resulting forward motion. So let me kind of go off a little bit and talk a little bit about systems and the environment. You've explored the acceleration given an object when a net force acts on it. A equals F sub net divided by M. You know that forces are exerted on objects by agents, and that forces can either be contact or long range. But what causes the force? If a rope pulls on a block, something or someone has to pull the rope. If you pull a rope, you feel the rope pulling you. Which is the object? Which is the agent? Long range forces are similar. If you play with two magnets, you feel each magnet pushing or pulling the other. Forces are pushing or pulling of two objects on each other. When a fast-moving baseball is caught, the motion of the ball is stopped. That requires force. A force the catcher exerts on the ball. But the ball also exerts force on the catcher, a force that can be felt. How do these forces compare? You've probably heard the answer: for every action there's an equal and opposite reaction. But what is an action and what is a reaction, and why are they equal? We previously talked about systems and environments, and I want to spend a little bit of time talking about that. A system whose motion you want to study is isolated, and agents that exert forces on the system are identified. Now consider two systems whose motion you want to study. They interact with each other as well as other agents. Recall that the environment consists of all the other systems whose motion is not being studied. So let's go back to our catcher's hand and the baseball. The ball is one system, the catcher's hand is the other. So what forces act on each of these two systems? The weight forces on the ball and the hand, and the force of the arm on the hand are considered external forces. The two forces, large F, sub, hand on ball, and large F, hand, ball on hand, are the forces of interaction between the ball and the hand. Notice the symmetry in the subscripts, hand on ball and ball on hand, or more generally, A on B and B on A. So the forces F sub A on B and F sub B on A are sometimes called the action-reaction pairs of forces. This suggests that one causes the other, but this is not true. The force of the hand on the ball does not cause the ball to exert a force on the hand. The two forces either exist together or not at all. So what about the directions and magnitudes of the forces? So according to Newton, an interaction pair is the two forces that are in opposite directions and have equal magnitude. The force of the catcher's hand on the ball is equal in magnitude and opposite in direction to the force of the ball on the catcher's hand. So let's illustrate it considering how a car accelerates. So first we treat the car as a system. The car touches the road, so the road exerts contact forces on the car. There is the upward normal force and the forward friction force in the direction of the acceleration. There is also the downward long-range weight force on the car. To keep the picture simple here, ignore forces on the rear car tires. But all of these forces are part of force pairs. If the road exerts forces on the car, then the car must exert equal and opposite forces on the road. Thus the car exerts a downward normal force and a backward friction force on the road. Finally, the car exerts an upward force on earth. These forces can certainly be confusing. You accelerate a car by pressing on the accelerator or the gas pedal. Through a variety of gears and rods, the engine turns the wheels. the wheels exert a backwards force on the road, but it is not this force that accelerates the car. First, it's in the wrong direction. Second, it's exerted on the road, not the car. It is the forward force of the road on the car that propels the car forward. If it weren't for the interaction between the car and the road, the car wouldn't move. If you've ever tried to accelerate a car on ice or on loose sand, where the frictional interaction is reduced, you can certainly appreciate the importance of Newton's third law. Thus, there is a backward force on the road and an upward force on Earth. As a result of this force, does Earth accelerate upward then? Let's go to our third learning objective. Describe how to identify a pair of action-reaction forces. Sometimes the identity of the pair of action-reaction forces in interaction is not immediately obvious. For example, what are the action-reaction forces in the case of a falling boulder? You might say that Earth's gravitational force on the boulder is the action force, but can you identify the reaction force? Is it the weight of the boulder? No. Weight is simply another name for what? The force of gravity. Is it caused by the ground where the boulder lands? No. The ground does not act on the boulder until the boulder hits it. There's a simple recipe for treating action and reaction forces. First, identify the interaction. So again, object A interacts with another object B. The action-reaction forces are stated in this form. Action, object A exerts a force on object B, and reaction, object B exerts a force on object A. So, to identify a pair of action-reaction forces, first identify the interacting objects. And if the action is A on B, the reaction is B on A. So in the case of the falling boulder, the interaction during the fall is the gravitational attraction between the boulder and Earth. If we call the action Earth exerting a force on the boulder, then the reaction is the boulder simultaneously exerting a force on Earth. So we will be talking about the horse cart system in our next flip video, where we will talk again about systems and environments, and we will be identifying the interacting objects A and B, the pairs, and then we will also be identifying systems as they all relate back to the environment. This ends flip video number 12. Thank you.